Good morning, Savio. Good morning, Alok. Good morning to all of you. In today's class, we are going to look at fluid mechanics and we are going to do a part of fluid mechanics which is called statics. Fluid mechanics is often a forgotten chapter in the study of physics, at least in 11th, 12th, and junior college, and sometimes even in undergraduate classes. People hardly give any attention to fluid mechanics, but it's a very important subject in our lives and in engineering. So let us do some proper justice to this subject, and that is why I have planned to take a couple of extra lectures instead of doing it in a very rushed out manner. So, what is statics? So, statics is the situation when the fluid is not moving, fluid is at rest. Sometimes, even this question is asked that what is fluid? A fluid is something which can flow. As you all know, air can flow, so it's a fluid. It's a collective behavior of many particles. Liquid is a fluid, so liquids can flow. So we study in fluid mechanics the collective behavior of many particles together. When they are not flowing, then that branch or that part or that domain is called statics. Basically, statics is defined by two laws, and they are called Pascal's law and Archimedes' principle. So here is an image of a fish. The fish's flesh density is higher than water. So normally we know that the dense objects they sink in water. The flesh of the fish has a density which is higher than that of the water. The question is still they can keep themselves afloat in water. How? So we will try to answer this question as we go through this chapter. Let us make the basic constructs needed. Density is one of the most fundamental concepts that we learn early in 7th or 8th grade. Density is mass upon volume. It is sometimes also called as mass density or simply density. Once you go to a higher level, you will study many other types of densities as well, like linear densities, areal densities, charge densities, etc. 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 Don't get confused. We are talking about the mass density, and the mass density is sometimes simply written as density. Unit is kilogram per meter cube. So 1 kg per meter cube is equal to 0.001 gram per centimeter cube. I have a small table here which gives the densities of various substances which we use in our day-to-day lives. Please check it. So air has a density of 1.2 kg per meter cube. Do remember because it is important for your calculations. One of the heaviest elements in our day-to-day life could be either of the things iron, brass or copper. which is around 7 or 8 into 10 power 3. At the center of a white dwarf star, density can shoot up to 10 power 10, while at the center of neutron star, density can shoot up to 10 power 18. You can see that there is quite a fluctuation in density which is available in nature. To obtain the densities in gram per cubic centimeter, you simply divide by 10 power 3, which is 0.001 gram per centimeter cube. We sometimes define a term called specific gravity. Many places or many problems you will hear it. Specific gravity of a material is ratio of its density to the density of water at 4 degree Celsius, which is 1000 kilogram per meter. Sorry for little mistakes. Fair enough. Specific gravity of a material is the ratio of its density. What happens? Specific gravity of a material is the ratio of its density to the density of water at 4 degrees Celsius, which is 1000 kilogram per meter cube. Good, that's the correct way. It's a pure number without units. It's a very misleading term also. There is nothing specific here and nothing of gravity. It is just the ratio of the two densities and it is just a number. So sometimes people get scared when they hear of specific gravity. They feel that it's some new term coming in. It is not. Specific gravity, when it is given, that means what is given to you is how many times the element is heavier compared to water. Heavier in a sense, dense. So when I say specific gravity of aluminum is 2.7, that means aluminum is 2.7 times more dense that of the water. The other thing that we have to remember is pressure. Pressure we know is that force upon area. But pressure at any point in a fluid is defined as normal force per unit area at that point. So it's very important to understand. Suppose if you are in a fluid, then to evaluate pressure, you have to first imagine an area around the point at which you are intending to calculate the pressure. Suppose I want to calculate pressure here. Imagine a little area dA which encompasses that point. Then you figure out how much is the force acting from the perpendicular direction. Once you know the force and you know the area, then pressure can be calculated. Pressure is dF upon dA. It is written as dF perpendicular upon dA. If you choose an area which is double a larger area, then the force can be larger. Therefore, the pressure would be the same. You can choose area in any orientation. So you can choose a vertical orientation, you can choose a horizontal orientation of the area. However, at this point, center point, the pressure will be same in all directions. It doesn't matter which way you are making the calculation. and the pressure is a scalar quantity. Pressure is normally measured in Newton per meter square, and another unit given to it is Pascal after Blaise Pascal. So 1 Pascal is 1 Newton per meter square. That means if you are applying a force of 1 Newton on an area of 1 meter square, it is called 1 Pascal. You just have to imagine what it is. 1 Pascal pressure is not a large pressure. For example, what would be the 1 Newton weight? Think about it. What would be the weight of 1 Newton? How does it feel? So the weight of 1 Newton, if you take a 100-gram object, then maybe a medium-sized apple, maybe a smallish to medium-sized apple, or a small guava, or a 100-gram weight, or a small mobile phone. These are all fall in that range of 100 grams. Then typically the weight of such objects you will get by multiplying by 9.8, which is roughly around 1000, which is 0.1 kg into 9.8, which is roughly around 1 Newton. So if you take one such object which has a weight of 1 Newton and keep it on a sheet, a plate which is 1 meter by 1 meter, or keep it on the table which has the dimensions of 1 meter by 1 meter, then typically the entire plate will experience the force in the downward direction, and we will say that the pressure exerted is 1 Pascal. It is not a very high force or a high pressure. It's a small pressure. Another quantity for pressure which is normally used is atmosphere, or 1 atmosphere, or atmospheric pressure. In terms of Pascal, it's 1.013 into 10 power 5. So it's a very high pressure value. Since we are all used to live in air pressure, this kind of air pressure, we don't experience it. Now here it is written as dF by dA, but if pressure is same everywhere, then it can also be written as F by A. So do remember that. Throughout in this chapter and in the next chapter, our next lecture, we are making two important assumptions. One is the fluid has uniform density. In case of, now we are doing statics, so we assume that fluid is uniform density. Next chapter or next class we will talk about dynamics, that is when the fluid is moving. Even there we will assume that the liquid has uniform, or the fluid has uniform density, or it is an incompressible fluid. What do we mean by incompressible fluid? An incompressible fluid is one which doesn't get compressed anywhere, because what will happen if it gets compressed? If it gets compressed, its density will rise. So we assume that those kind of things doesn't happen and the fluid remains uniform in density. This assumption is fairly correct for our day-to-day living experience, but they fail under extreme pressure situations or some specific kind of fluids. The other assumptions, which is more important for dynamics, is that the fluid must not rotate. We will talk about it in the next class. So I have a fluid here in a flask. Now if you take the point at the top, then at the top the pressure on the fluid will be there due to the atmosphere above it, or due to the atmosphere simply. This pressure is P0. If you go anywhere inside the fluid, then at a point which is inside, the pressure is due to two reasons. It is due to the external atmosphere, obviously, but it is also due to the height of the liquid column. The liquid from here to here will exert an extra pressure at point P. So if I call in general pressure at this point as P1 and pressure at this point as P2, then P2 minus P1 is equal to, or the pressure difference at these 2 points is equal to minus rho g y2 minus y1. This is a very easy calculation or derivation, and if you think more you can do it, so I'm not doing it. Typically this difference in the y coordinate can be written as h, and therefore it can also be written as rho gh. So what? So P is equal to P0 plus rho GH. So P is, let me rewind, let me revise. P is the total pressure at this point in the fluid, at any point in the fluid. It is equal to the sum of the two components. What are those two components? The atmospheric pressure and the pressure due to liquid column height, that is H rho g. This ensures, or this explains us, that as you go through this liquid, a pressure gradient exists in the liquid column along the vertical. So if there is a liquid column, then the pressure gradient does exist, in a sense that if I take any two vertical points which are separated by say y2 minus y1, then the pressure gradient or pressure difference will be P2 minus P1, which is equal to minus rho g. So if I make my y interval infinitesimally small as dy, and the pressure interval also becomes infinitesimally small, then the pressure gradient, that is rate of change of pressure with respect to height, which is dp by dy, is equal to minus rho g. What does minus sign suggest here? The minus sign suggests that as y coordinate decreases, that is as you go down, the pressure increases. So the behaviors are in opposite direction. Why do we get this gradient? We get this gradient because of the gravity. The acceleration due to gravity works downward. The weight of each particle of the fluid works downward. That gets accumulated and that adds to this, and that becomes the reason for this gradient. Is there any way by which we can get a pressure gradient along say x-axis, along the horizontal as well? Is there any way? Answer is indeed there is a way. The hint is the acceleration. We get a gradient along the vertical because of the acceleration due to gravity, which works in vertical ways. Now, if the beaker and the flask is accelerated horizontally, say towards the right, then there will be a pseudo acceleration working on each particle towards left, and that will create a pressure gradient along the horizontal. So if the beaker is kept in a moving vehicle which is accelerated in one direction, then in that case you will get a pressure gradient along the horizontal axis as well. The result of the previous discussion is summarized in this diagram. In this diagram, if you notice, there are liquid columns of different shapes. This is straight and a sphere, this is some helical, this is thicker tube. But what is common to all of these? What is common to all of these is that the height of the liquid column is same in all the three. So it does not matter what their shape is. At any point, for example, if you take a small element of this, then the liquid column height or the length of the liquid column will have two components, the horizontal component and the vertical component. All the vertical components will add up to give you the height of the liquid column, and it is going to be same in all the columns, and therefore the liquid column height is same, and the pressure at the bottom at this point and at this point and at this point and at this point is going to be same, and that leads us to what is called as Pascal's law. The Pascal's law says the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessels. So if you have pressure applied in a fluid, then that pressure does not, it is not that pressure varies from position to position. The pressure changes and, sorry, the pressure spreads and it becomes same everywhere. And remember, we are talking about a condition of statics where fluid is not moving. It is not true when the fluid is moving. So, in fact, all the problems involving fluid mechanics, when you have to solve, when you get face a problem on fluid mechanics, you just have to ask one question to yourself. Is it a moving fluid or is it a static fluid? If it's a moving fluid, then if it's a static fluid, then you apply Pascal's law, Archimedes principle. If it's moving fluid, then we will see in the next lecture. So the pressure everywhere is same. That is what Pascal's law says. So if you have 2 points in a fluid, say point 1 and point 2, so all it says is that the pressure at the 2 points are going to be same no matter what force and area combination you have. So if force and area at point 1 is F1A1 and at point 2 are F2A2, then F1 by A1 is equal to F2 by A2. This can be used for lot of important ways. One of the ways it is used is to create hydraulic lifts. Many of you have done this as your one of the projects in your this section. So here there are two arms of this hydraulic lift. This is the smaller, thinner arm, and this is a larger or wider arm. So you have two forces acting here, F1 and F2, and here there are two areas, A1 and A2. You can see that if A2 is much larger than A1, then F2 will be much larger than F1. Since this area is much larger than this, the F2 is much larger than this one. That what does that mean? This means that if you apply a small force here, you will get a large force upward here. So this particular thing is called hydraulic jack. Hydraulic jack is used to lift heavy objects by applying a small force here. The other example is a hydraulic lift. of course, which is more or less like this: hydraulic hammers, hydraulic brakes, etc. So there are a lot of examples of this use. Then we talk about absolute pressure and gauge pressure. We have just seen that the excess pressure above the atmospheric, the pressure, we have just seen that pressure at any point in the fluid is sum of the two components. That is the atmospheric pressure and the fluid pressure. So the fluid pressure is the excess pressure over the atmospheric pressure. Atmospheric pressure is there everywhere. It works on all the points. Fluid pressure keeps varying, and that is an excess. So this part of the pressure equation is called gauge pressure. So please remember this. While the total pressure is called absolute pressure. So this plus this. This can be used again to measure the pressure. There are multiple devices which can be used to measure the pressure. One is an open tube manometer. So an open tube manometer, how does it look like? So in a very strict sense, it is a U tube containing mercury. If you want to find the pressure of a certain device, then you have to attach that device, say a balloon, to the one end of the manometer. Because of the pressure inside, the level here goes down, level here goes up. You find the difference in the two level and multiply by rho and g to get the pressure difference. So this is one way. A mercury is a very heavy liquid. So with use of mercury, this becomes very small in size. But there is no restriction on you to have it only from mercury. For example, you can use a U-shaped tube, water plastic tube, fill it with water and attach a balloon on one end, and you can measure the pressure inside the balloon by knowing the difference of the water column. Just that the water column is has a smaller range than the mercury because water is a lighter fluid. This is a mercury barometer. Again, the mercury use of mercury makes the things smaller in size. You can make a barometer by using any other liquid for that sake. Just that the height of the column sometimes becomes too large. So for example, if you make a water barometer, the height of the column will run to 13 or 14 feet. So if you have a two-floor home, maybe you can try that. So all you have to do is you take a tub of the liquid, use a tube of the liquid, fill it completely, invert it and leave it. The atmospheric pressure works on the tub water or tub liquid while the mass of the liquid column acts downward. Soon an equilibrium will achieve and the height to which the liquid, here mercury, rises depends on how much atmospheric pressure is there. So by knowing this height, you can measure the atmospheric pressure. And this area does not have any fluid. So it is a near vacuum at the top of the tube. This experiment was first performed by a famous scientist named Torricelli, and that is why we we measure the pressure inside a vacuum or vacuum like situation in terms of torr. The unit is called torr. So one torr is 1 millimeter of mercury. So 1 millimeter of mercury is a very small height, so it's a very low pressure. General atmospheric pressure is how much? So as we all know, at sea level, the atmospheric pressure is 75 or 76 centimeter of mercury. This is an industrial pressure gauge which is used at many places, cycle stores, petrol pumps, etc. So all you have to attach it and it gives you the pressure. So the pressure that you want to measure acts down inward, which actually rotates uh, a dial here, and the scale is calibrated. It is called Bourdon pressure gauge. That brings us to the last topic of today's class, which is the buoyancy. Buoyancy is credit goes to the famous Greek philosopher Archimedes, who worked in many branches of science. Archimedes' principle says that when a body is completely or partially immersed in a liquid, the fluid exerts an upward force on the body which is equal to the weight of the fluid displaced by the body. So it's a very common and very interesting principle. You people have must have read it first in 7th or 8th grade. Let's explore more. So it is summarized in these two drawings. Let us look at the left drawing first. We have some liquid in a beaker. Now, just imagine an arbitrary element of the liquid inside the beaker. This is an arbitrary shaped, arbitrarily sized liquid element. Also, remember our assumptions. Our first assumption is liquid is at rest. We are dealing with static situations only. Remember the second assumption. The liquid density remains unchanged. Now, according to Pascal's law, each point in the liquid, any point if you take, it will experience a pressure in all directions. So, for example, I take a point here at this point. So, it will experience, of course, a pressure downward, but it will experience a pressure upward as well. So I am trying to find out that how much pressure and hence how much force will work on the surface of this chosen element. So if you are here, there is a force which is going to work in the upward direction, normal to the surface. If you are here, normal to the surface, a force will work in this direction, so on and so forth. So if you are here, normal to the surface, a force will work in the downward direction. So on the entire surface from outside, a force is going to work in a direction which is perpendicular to the surface of this chosen element. So the big question arises, and that is this: what is going to be the sum total of all these external forces? Now it's little challenging to calculate it analytically. You will have to take components everywhere and see what happens. But then I can give you a very easy way out of it. The sum total of these forces has to work in a direction which should be upward. Why should it be so? Think about it. The entire fluid element will have some mass, and the weight of this fluid element will work in the downward direction. Now, we have made a very important assumption that the fluid is static, it is not moving. So, on this element of the fluid, there is a weight, or which is a force working in the downward direction, but still the fluid is not moving. To be very strict, not accelerated. Then there has to be a net force, there has to be a force working in the upward direction which must balance this downward weight. So this upward force is the sum total of all these forces, and these two are equal and opposite, and they cancel out, and that makes the fluid element static inside the fluid. So this is a very loose explanation. You can have a very rigorous explanation also. For example, if you take this component, you find out the vertical component, you find the horizontal. Vertical works upward, horizontal works downward. Take this one, find the vertical, find the horizontal. You can see that the horizontal here works leftward, horizontal here works rightward. Both the horizontal components will cancel, vertical components will survive. Similarly, you can do for forces in the upward section also. You would realize that the force in the downward section is more than the force in the upward section. You can sum all over and you can get the net force working in the upward direction. This is called force due to buoyancy. The sum total of all these forces works in the upward direction, and that is called force due to buoyancy. Now, imagine that we remove this fluid element by a similarly shaped solid. I assume that the solid has uniform density so that the center of gravity is at the same place as that of the fluid. But now the fluid is gone and you have a solid. Now the solid may have a higher density than the liquid element, or it may be having lesser density. Depending on what is the density of solid, that will decide how much weight the solid is exerting downward, or how much weight acting, how much is the force acting downward. But what decides the buoyancy? Upward force. So upward force is decided by sum total of all these forces. Now if the shape of the solid is same as the shape of the liquid, then the sum total of all these forces in the upward direction would remain the same as in the previous case. So as you go from this case to this case, the upward force is the same, but the downward force, it may vary. It can increase, it can decrease. So for a solid for which the density is high and downward force is more, the solid will accelerate in the downward direction. It will start sinking. For a solid whose density is less, on that the upward force or the buoyant forces will be higher and will start moving upward and it will remain afloat. And that is how certain objects, certain things, they float on the liquid surface. That is how the boats float on the liquid surface, because inside major is air, majority of the matter, and the average density, although the boats are made up of mostly steels these days, the average density is going to be less than the solid, less than the water, and they remain afloat. While if you have a solid rod of metal, it will sink. Other examples are a floating balloon. You know that helium balloons, etc. If you have a helium balloon, then the density inside the balloon is very less. Outside buoyant forces are same as that on a normal balloon. But a normal balloon may go down on the floor somewhere very slowly. A helium balloon goes up. Remember our opening question was a floating fish. So how do a fish float? Even if the flesh density is higher than that of water. So what fishes have is air sacs inside their body. In their bodies, they have air sacs whose volumes they can control. They can throw the air out, or they can absorb the air which is dissolved in water and increase the capacity of that air sac in their body. So by adjusting the volume of the air in the air sacs in their bodies, they control their average density. The flesh density is higher, but because of the air sacs, the average density is less compared to the water, and because of which the fishes can remain afloat. So if they have to come up, they have to take more air and they can come up, and if they have to go down, then they expel the extra air and they go down. If you have a fish tank, you can observe this phenomena if you observe carefully. The another example of buoyancy is a hydrometer. A hydrometer is an instrument which is used to measure the density of a liquid. So it works on using Archimedes' principle, compares the density of any fluid or any liquid with water, and more on this in the reference book or on the internet. It's a very simple instrument to make and design. So we can stop here. We have finished our discussions on statics. In the next class, which will be in the evening, we will discuss about fluid dynamics. Thank you.